So now we're on to Viola Gelli.
Yes.
So if you could share your screen.
So can you see it?
Yeah, we are good.
Okay, so I can start. So hello everyone, I am Viola Gelli, a second-year PhD student at the University of Florence, and today I'm going to tell you about dwarf satellites of high-redshift Lyman Break Galaxies, a free launch for JWST. So let me spend first few words on about why we are interested in dwarf galaxies at high redshift, and that is because they are the first galaxies that form in the universe, and they also represent the building blocks for the formation of more massive systems that we see today. And we know that JWST will provide for the first time direct observation of these faint objects, observing them directly during the epoch of reionization. But what do we know at present about these systems? Basically, our knowledge of dwarf galaxies comes mainly from detailed observations in the local group, and we know that here they live mainly as satellites of more massive systems like our Milky Way and Andromeda. And at high redshift, actually, we expect a similar situation. So we expect to find dwarf galaxies not only isolated in the field, but also living as satellites of typical massive systems there. So those are those massive galaxies that are typically observed as Lyman Break Galaxies. So this is a good news, let's say, because we know that already within the first surveys that JWST will perform, many Lyman Break galaxies will be observed. So we asked ourselves, will JWST be able to detect for the first time the satellites of the massive Lyman Break galaxies? To answer this question, I used an high-resolution cosmological simulation developed by Pallottini in 2017. And this simulation reproduces the properties of a typical Lyman Break galaxy up to redshift 6. And here I show you a stellar density map of the galaxy, which is called Althea. And here in the center, you can see the face-on disk. And what I found is that inside the virial halo of Althea live 6 satellites. Their masses cover a wide range from 10 to the 6 to 10 to the 9 solar masses. And actually 5 of them are dwarf galaxies in the sense that they have their own subhalo of dark matter. But one of them, the smallest, S1, do not have dark matter, so we labeled it as something more similar to a protoglobular cluster. So in this first paper that was published last year, I studied in details the physical properties of these satellites, so these dwarf galaxies that live in these peculiar dense environments around Lyman Break galaxies, and I now go through the main results. So I wanted to understand which mechanism drive the evolution of these systems, so I derived their star formation and metal enrichment histories. And I found that their behavior can be divided mainly into 2 categories according to their mass. Indeed, on one hand, we have the behavior of low-mass satellites. Here I show you the age metallicity relations, along with the star formation history and the metallicity distribution function. So we see that these bone systems form all of their stars in 2 short and intense bursts of star formation, during which the metallicity increases in time. Also, we may notice that there is a first interruption of star formation and then a subsequent quenching, and both these features are due to the effect of the internal supernovae feedback. So it is indeed the internal supernovae feedback which is responsible and capable of completely suppressing the star formation in these small systems. On the other hand, we have high-mass satellites, which can form stars for much longer times, and their metal enrichment history is more complicated, characterized by all these vertical trends, and each of them represents a merger event happening. So we have that merger events that are very common in these highly dense environments are the mechanism that counteract the effect of internal supernovae feedback and can allow star formation to go on for longer times in these massive systems. We also may notice that both type of satellites are very rapidly enriched up to solar values. So these systems are typically more metal-rich than typical dwarf galaxies that live isolated in the field. But if we check the amount of metal-poor stars composing their stellar populations, so these, we have that lower massive systems have a higher amount of metal-poor stars. Indeed, if here I plot the fraction of metal-poor stars as a function of the halo mass for the 6 satellites and for the central LBG, and these clearly show a decreasing trend, meaning that lower massive systems are dominated by metal-poor stars. So now that we've seen the main evolutionary and chemical properties of these dwarf satellites, we can move on to answering our main question. So will the stellar emission of these objects be observable with JWST? So with this aim in mind, I modeled the stellar emission and dust absorption of each system. And here I show you the spectra of the satellite along with the one of the central LBG Althea. And I chose to show you these spectra for 2 relevant stages during the evolution. Indeed, at redshift 6.5, we have that the low mass systems are experiencing their short burst of star formation. So in this stage, their spectra, as you can see here, are peaked at a lower wavelength. Here, instead, at redshift 6, they had already been completely quenched, as we saw before, by supernova feedback. So their spectra are passive, so are fainter and dominated in general by older stellar populations. Also, we may notice these horizontal lines that represent typical sensitivities for the NIRCam instrument on JWST, and this gives us an idea of what we'll be able to detect. For instance, if you remember the small protoglobular cluster which I showed you before, we have that its emission is not shown here because it's well below these limits, so it will most likely not be detectable. But all the other satellites have fluxes comparable or above these limits, meaning that they will be detectable. However, to understand if their emission will effectively be resolved from the one of the central LBG, I needed to consider also the spatial resolution of the instrument. So here I show you these synthetic images of the system at redshift 6, as will be observed with the near-infrared camera of JWST. I show you the result for 2 filters and 2 different exposure times, where 20 hours is the typical time that will be reached by the deepest surveys with JWST. And these images show that the emission of all the 5 satellites will be observed in 20 hours of observation, but also that in just 3 hours it will be possible to catch the light from the 2 most massive systems. Also, we see that if a system is located below about 0.2 arcseconds, so like in our case, the satellite S5, it will be difficult to disentangle its emission from the one of the central galaxy Althea. But all the other galaxies are actually well resolved, so we will be able to easily identify these systems as dwarf satellite galaxies. At this point, we also took a step farther, and we wanted to try to understand if already just with imaging and photometry, it will be possible to derive some properties of the satellites. So I produced these color magnitude diagrams that show us how the colors and magnitude of the systems change during their evolution. And these are color-coded according to different physical quantities. So what we learn from here is that, for instance, we found that satellites with this color below minus 0.25 will identify star-busting low-mass dwarf galaxies, which are dominated by young and metal-poor stars. So here I leave with you my conclusions. Basically, the takeaway point is that we study these new class of high-redshift dwarf galaxies, which are different from those living isolated in the field, because these ones live in dense environments as satellites of massive Lyman Break Galaxies. And we demonstrated that they will be observed already within the first starbase with the NIRCam instrument, and also they will be easily identified in the surrounding of Lyman Break Galaxies, hence providing a free lunch for JWST. Thank you. I'm happy to take questions.
Thanks. That's yeah, very interesting simulations. Yeah, so if you have any questions, you can post them in the Slack. So just a quick question of clarification, I guess. The star formation model does account for a metallicity dependence, or in some way, or H2? Yes.
Yes, sure. When I model the spectra, I take into account the age of the stellar population, the metallicity, and also.
I was asking more about the actual star formation recipe in the simulation itself.
Yes, it takes into account the metallicity. Yes, but also yes, I meant also for the modeling of their CD. Of course, I took into account all of that.
Yes, great. Mm-hmm.
So there's a question in Slack asking, how lensing
Sorry,
can help
I can't
boost
hear
up
you
the detectability. Sorry,
I didn't hear
you. It will be good to estimate how lensing can boost up the detectability.
Yeah, sure. That will be really interesting, because it will definitely boost. But actually, we know that, for instance, within the JWST surveys, there will be no lenses. But already without lensing, we can do, so much. So even without lensing, here we see that many dwarf galaxies will be resolved in also more than 1 pixel. And so they will be easily identified. And also one thing that I did not say is that these images that I show here are for redshift 6, which, if you remember, is the phase when these galaxies are passive. So this is the faintest stage, let's say, during the evolution of these galaxies. So already at the faintest stage, we will be able to identify them. So even at, let's say, as previous stage with respect to redshift 6, the emission will be even more. So it will be possible even without the lensing.
Next question is, do you have any ideas to distinguish the satellites and star-forming clumps with a galaxy with JWST?
Do you mean to distinguish, yes, satellites from star-forming clumps?
Yep.
Okay. Well, actually, that was the point of, let's say, the fact that the prosoglobular cluster, the one that we called prosoglobular cluster, is actually just a clump of also gravitating stars. But the main difference, physical, of that object and our satellites is that within the simulation, it has no dark matter at all. While our satellites do have their subhalo of dark matter. And actually, our results tell us that these galaxies that have their halo of dark matter will be observable, whilst typically prosoglobular cluster and I think also small clumps within the halo won't be observable, because their flux will be much lower, let's say, with respect to these limits. And also, of course, there's this problem of, clumps living within the disk will be difficult to disentangle their emission just for a resolution problem. So I think those independent objects located in about 0.2 arc seconds will be definitely dwarf satellites, galaxies.